Alright class, so we've been talking about IR and NMR and how to look at the spectrum and figure out what is the structure of your compound. Now let's put all the pieces together. What we're going to do today is a practice session. We're just going to put up different spectrum and figure out what is our compound. You ready to do this? Let's do it. Alright, here is our first spectrum. Again, you have a copy of this, so take out your copy and then do it with me. Now, when you look at this, the first thing that is going to stand out to you is that you have the formula. That is great that I have the formula. Okay. Now, let's play around with the formula. Again, you have a copy of all the practice problems I'm putting up today, so you can take out your copy. The resolution will be better. If you remember, we said number of carbon times 2 plus 2 gives me the number of hydrogen. So I have 4 carbons. 4 times 2 is 8. That would be 10 hydrogen. And then you add 1 hydrogen for each nitrogen you have. I have no nitrogen. You subtract the hydrogen for each halogen you have. No halogen. You don't do anything for oxygen. So this is the 10 hydrogen I would have if I have nothing but single bond. If nothing but single bond. But how many I actually have? I actually have 8. So what does that mean? That means I lost 2 hydrogen to end up with 8 hydrogen. So I lost 2 hydrogen. So I probably have a ring or a double bond somewhere in the compound. So far so good? Okay, so we know we're missing 2 hydrogens, so we're looking at a double bond or a ring, not a triple bond, because triple bond you would lose 4 hydrogen, not a benzene ring because I would lose 8 hydrogen, but all I lost right now in this case, I only lost 2 hydrogen. So far so good? Okay, again, this formula will also give you a lot of information. Now I'm going to look at the IR. I want to look at the IR. The first thing I'm going to say, again, remember what we said, IR, what you don't see is just as good as what you see. When I look at the IR, I go, okay, I have no OH here. So I know my oxygens are not from the OH. That's good. That's good to know. Now, when I look over here, I was like, oh, that's the carbonyl. So I have a carbonyl. Okay, that's pretty good. I have no triple bond. I already knew that based on the formula, but again, more confirmation is always nice. So the 2 things that stands out to me, no OH, because I know I have an oxygen, so I'm not looking for alcohol, and I have a carbonyl, which means that would account for me losing 2 hydrogen. Alright, so that's what the IR is going to tell me. Now, this one is Proton Nmr, and this one down here is Carbon Nmr. We're not going to go over Carbon Nmr in this class, but I just put it under so you know what a Carbon Nmr looks like. So Proton Nmr is what we are going to look at. And remember what we said last time. We said that when you look at Proton Nmr, there are 3 things I need you to look at. Chemical shift, integration, spin, splitting. Those are the 3 things I need you to look at. Okay, I'm going to come over here. I'm actually going to write those down. I need you to look at chemical shifts, and I give you this handout. Then integration, so you know how many hydrogen per peak, and then spin, splitting. Look at, you have singlet, doublet, what kind of peak you have. Those are the 3 things you should look at for NMR. And also keep in mind that NMR will give you a peak for each unique set of protons, right? So what we have, again, and I want to write this down too, we have 1 peak for each unique set of protons, and that really matters because then we can confirm our structure by looking at how many unique sets of protons we have. Alright, I have, how many peaks do I have? I have 3 peaks here, right? I have 1, 2, 3 peaks here. You guys agree? Okay. I'm actually going to label them A, B, C, from left to right. Okay, 3 peaks. When I look at the peak over here, I want to look at the chemical shift. I go, this is around 4 ppm. To be around 4 ppm, that means the carbon that the hydrogen is attached to it should be directly attached to an oxygen, right? So if that carbon is directly attached to a hydrogen, case over here, that's when I'm going to get around 4 ppm. So when I see this, I'm going to actually make a note of myself. It's like, okay, so that means the carbon that has the hydrogen is directly attached to an oxygen. So far, so good. Okay. So that carbon is directly attached to an oxygen. That's why it's at 4 ppm. That's why it's so downfield, because the oxygen is pulling the electron toward itself, which means that hydrogen is kind of de-shielded because it doesn't have that much electron cloud to protect it against the magnetic field. All right. So far, so good. We're good. Then I'm going to look at this one. I'm going to say, okay, this is at 2 ppm. What did we say if you have a 2 ppm? If you have a 2 ppm, usually means that that carbon that the hydrogen is bonded to it is attached to a carbonyl, right? I'm going to come over here. So when I have the case right, where is it? Right here, okay? So the carbon is not directly attached to an oxygen, but the carbon is attached to a carbonyl. That happens at about around 2 ppm. So what I know here is probably this carbon is attached to a carbonyl and is not directly attached to an oxygen. That's why it's 2 ppm and not 4 ppm. So far, so good? Okay. Now, I'm going to look over here. About 1.3 ppm. So, just a CH. Nothing too interesting. Now, when I'm looking at this, I go, hold on a second. I just accounted for the 2 oxygen that I have. I have 2 oxygen. I know it's not an OH. I know I have a carbonyl. And probably the other one, I have a carbon that is directly attached to an oxygen, but is not an alcohol. So it's probably an ester, right? It's not a carboxylic acid because I don't have an ugly OH. Okay. So this is a lot of information. This is not bad. So now let's try to put them together. So I looked at chemical shifts. Let's look at integration. When I look at the integration, this peak has 2 hydrogen, 3 hydrogen, and 3 hydrogen. Okay, not too bad. Now, peak A, what's the splitting? Is a quartet. So, what I know about peak A is that the hydrogens that are attached to the carbon, that carbon is attached to an electronegative atom oxygen, and that's why it's at 4 ppm. Okay, so what this is, I'm going to write it in, let me write it in blue. So I'm going to have a CH2, and this carbon is bonded to an oxygen. That's why it's downfield. So far, so good. How did I figure it's CH2? Because the integration is 2. So the hydrogen on this carbon that is directly attached to an oxygen, so it's 4 ppm, and it's a CH2 because the integration over here is 2. Stay with me. This is the first time we're doing a big problem, putting every piece together. Now, what is this splitting? It's a quartet. If you are a quartet, probably your neighbor had how many hydrogen? N+1 rule. If you're a quartet, your neighbor had 3 hydrogen. 3 plus 1 is 4. So maybe this one is attached to a CH3. Okay? And these are more hydrogen for peak A. That makes sense. So if peak A is a CH2, that's my integration, is attached to an oxygen, this carbon is attached to an oxygen, electronegative, 4 ppm, and is a quartet because the adjacent carbon has 3 hydrogen, 3 plus 1, N+1 rule would be 4. I have a quartet. I feel pretty good about this so far. Yeah? Okay. Now, let's look at peak B. So we said that for peak B, the hydrogen is attached to this carbon. This carbon is attached to a carbonyl group. That's why it shows up around 2 ppm. Okay. Now, how many hydrogen? 3 hydrogen. So 3 hydrogen. So I'm just going to write things down. Just write things down, see how it goes. So I have 3 hydrogen. So maybe I have a CH3. And, I don't like to write it this way, because I like to show what's... And that CH3 is attached to a carbonyl group. Would that make sense? Let's see if that makes sense. So I said I have 3 hydrogen, so maybe I have a CH3. Is at 2 ppm, which probably means it's attached to a carbonyl. I know I'm looking for a carbonyl, so this is a carbonyl it's attached to. Now, does the spin-spin splitting make sense? That would be a good conformation. If you look at this, the adjacent carbon has no hydrogen. The carbonyl has no hydrogen. So what type of peak would you expect? You expect a singlet. Oh, look at that. We have a singlet, don't we? Okay. So this would be maybe my B hydrogen. So far, so good. Okay. Now, for C, I know it's some sort of carbon with hydrogen, right? And it's probably a CH3 because I have an integration of 3. Okay. So I've got these pieces. And pieces really, really help you to figure things out. So what are the pieces I have? The pieces that I have a piece here that I think that's going to be. I have a piece over here, and I have a piece over here. Okay. Now, here we said this hydrogen, this CH2, is probably attached to a CH3. That's why we get a quartet. Well, I have a CH3 over here, don't I? Could that be this peak over here? Let's figure it out. This CH3 is attached to a CH2. So the adjacent carbon has 2 hydrogen. If the adjacent carbon has 2 hydrogen, 2 plus 1 would be a triplet. Is this a triplet? Yes, this is a triplet. Okay, so now I have all the pieces. I have to put it together. The other piece of information that I want you to pay attention to is the formula. Always go back to the formula. The formula really, really helps you. In this formula, how many carbon you're looking for? You're looking for 4 carbon, right? You're looking for 4 carbon. You're looking for 4 carbon. Go, okay, I have 1 carbon, I have 2 carbon here, I have 3, I have 4 carbon. Okay, my number of carbon matching up. So look at the formula. The formula can be very powerful, helping you figure things out. Okay, so now we have to put everything together. Can we do this? We can definitely do this. All right, how about this? How about this is my compound? Would this make sense? This would make sense. This is my A peak, this is my C peak, and this is my B peak. Does the number of carbon and hydrogen make sense? 1, 2, 3, 4. Yeah. 1, 2, 3, 4, 5, 6, 7, 8. Whoosh. That makes me feel better. Number of hydrogen counts. I have 2 oxygen. So the formula matches up. This has C4H8O2. The formula matches up. That gets the smiley face. Does the integration match it up? It totally does. Next to electronegative atom. So this is 4 ppm. Next to a carbonyl. Not as electronegative because oxygen is a little bit farther away, but it still is pretty. It makes it to be downfield 2.0. And then I have a CH3 here. So this matched up. Yeah? Okay. Again, this is the first one. I don't feel overwhelmed. We're going to do a lot of this practice problem to make sure you get this down. Okay, let's do another one. here is our next problem. Again, you have all these practice problems that I'm putting up here. You have a copy of them. I posted all these problems. So make sure you have it in front of you if the resolution on my screen is not the best. All right, so let's do this one together too, right? Let's do it together. So what's the first thing you're going to look at? I give you a formula. That sounds pretty good. Let's look at the formula. I have 4 carbon, so number of carbon times 2 plus 2, that gives me what? 10? Yeah, okay. Don't do math in your head, use a calculator. Okay, so I have 10 hydrogen. If I had nothing but single bond, okay? Now over here, I also have only 10 hydrogen. Right here, so there's no hydrogen that I have to subtract for, so the formula also has 10 hydrogen. That's great. That means I'm not looking for double bond, I'm not looking for a benzene ring, I'm not looking for triple bond. Everything is saturated, everything is single bond. That's great, right? So I know already that I have no double bond. I'm not looking for any double bond. That's a good piece of information to have. Okay. Now, I didn't give you the IR, but that's okay. I give you a formula. You know, there's like no double bond. That's nice. I have 4 carbon, I have a hydrogen, and I have an oxygen. Now, what are we going to do? Let's look at NMR now. How many peaks do we have? I'm going to label the peaks. We have a peak here, A, B, and C. This is just a blown up of that. We just zoomed it in. So I have 3 peaks for the NMR. The first thing you're going to do, you are going to look at the chemical shifts, right? Let's look at the chemical shifts. Peak A is pretty upfield, pretty downfield. It's about 3.6, 3.5 ppm. Okay. Now peak B is also downfield, so they're all over 3 ppm. I know I have an oxygen, right? So the oxygen is probably what's making those to be de-shielded. And then I have the peak C, that's about 1.2 ppm, and it has 6 hydrogen. Okay, so those are the chemical shifts that I have. Now I know I have an oxygen, I know I have 4 carbon, I know everything is single bond. Now I need to kind of put all the pieces together. And again, this one down here, this is carbon NMR. We're not going to look at carbon NMR for now. This class, we're going to focus on hydrogen NMR. Now, what am I going to do? So this peak over here, the peak over here is a CH3 probably, right? I have 3 hydrogen, so I'm going to draw a CH3, and then it's probably attached to an oxygen, right? Because this is downfield. This is the most left peak that we have. I want to say this peak is probably attached to an oxygen. So far, so good. Okay. Now then, we have this one, which has only 1 hydrogen. So this is a CH. And probably this is also attached to an oxygen because it's around the same ppm, right? It's about 3.4, 3.5 ppm. Okay. And it's a CH. It has only 1 hydrogen. Then over here, I have 6 hydrogen. Now, if I have 6 hydrogen, what's the most likely case? If you have 6 hydrogen, what's the most likely case? That means you probably have 2 CH3s that are equivalent to each other. Okay? Because I have a peak that has 6 hydrogen associated with it. So one of the options, and the most likely option, is probably I have 2 CH3s and those are equivalent to each other. Okay. All right. Now, and this CH3 is a doublet. Now, what does that mean if you are a doublet? If you are a doublet, that means your adjacent carbon has how many? It has 2 hydrogens, right? Okay. So, sorry, it has 1 hydrogen, so N plus 1. So 1 plus 1 would be 2. Okay. So I'm thinking this is a 6 hydrogen. So I have 2 CH3 that are equivalent to each other. And then they are next to a CH because N plus 1 rule, right? The adjacent carbon has 1 hydrogen. 1 plus 1 will be 2. So I end up with a doublet. Well, look over here. Don't I have a CH over here? So is it possible that these 2 are attached to that? What do you think? Anything is possible, right? Okay. Let's draw it out. I'm going to have a CH3 and then CH3 attached to a CH. Okay. Now, if I do that, then that would account, these would be my C peak, and this is my B peak. Okay. That means there is 1 peak left, the A peak. And we said probably the A and B are attached to an oxygen, right? So this is probably attached to an oxygen. And what is attached to this oxygen? I have a CH3 attached to an oxygen. And this would account for peak A. Does this make sense? This does make sense, huh? Again, come to pieces first. First, we knew we had no double bond. That was great. Then we knew we have 1 oxygen, okay, based on the formula. I come over here. Peak A is downfield, so it's probably attached to an oxygen. Peak B is also downfield. It's probably directly attached to an oxygen, right? And then over here, I have 6 hydrogens, so probably I could have 2 CH3 that are equivalent to each other. Now, I know that I only have 1 oxygen. So if I only have 1 oxygen, it probably makes sense that CH3 and then CH2, these 2 are attached to the same oxygen. They're attached to the same oxygen. Yeah? Okay. Now, there's one more thing I want you to do to confirm that indeed this is our structure. Let's look at the splitting. So we looked at the splitting for this. This made sense. The adjacent carbon had 1 hydrogen, N plus 1. 1 plus 1 is a doublet, and we got a doublet. Whoosh. That makes it feel good. Okay? Now, peak A, does the splitting make sense for that? Peak A is a singlet. If you're a singlet, that means your adjacent compound does not have any hydrogen. Does that make sense? That makes perfect sense. This is attached to an oxygen. This has no hydrogen. So this is a singlet. It's not next to anything that has a hydrogen. This makes sense. Now, does B make sense? Now, this one, on one side is no adjacent carbon. On the other side, the adjacent carbon have 1, 2, 3, 4, 5, 6. And remember, the adjacent carbon have hydrogen. These 2 hydrogen are equivalent to each other. That's really key. We've talked about this. So HB, the adjacent is adjacent to C and adjacent to C, right? Is adjacent to HC and adjacent to HC. Now the key is that these 2 are equivalent to each other, right? These 2 are equivalent to each other. You know what? Let me rewrite this in a little bit nicer way. So, HB is attached to a CH3 and attached to a CH3. And these are equivalent to each other. They are from 1 peak, right? Now, because these are equivalent to each other, you can add them up, right? We talked about that. If the adjacent carbon have hydrogen, those hydrogen are equivalent to each other, they are additive. We can add them up together. So what would be the N plus 1 rule here? The N plus 1, the N would be 6. because I could add this together because these are equivalent to each other. 1, 2, 3, 4, 5, 6. So it would be 6 plus 1, that's 7. You have a heptad or it's called a septet. So we usually just call it a multiplet. I usually just call it a multiplet. When I have more than 6, I'll just call it a multiplet. And that's what you see over here. You see a multiplet. Now, you might be asking me, how come I don't see all the 7 peaks over here? How come I'm not seeing all the 7 peaks? Well, because this B peak is overlapping with peak A. So some of these 7 lines are hidden behind this peak. Yeah? Okay. This was a big problem. I'm going to repeat the last part. I just want to make sure you're on the same page. So, we knew we expected a multiplet. To be more specific, I'm looking for 7 peak. I don't really see 7 peak here, but that's okay. Because this peak is overlapping with peak A. So, some of them are kind of underneath that. Yeah? Okay. So, this is our final structure. This is our final structure. Not too bad, not too bad. Alright, are you ready for the next one? Okay, let's do next one. Here our next problem. Now do me a favor, pause this video, work on this one, work it out, see if you can get the structure, and then watch the video and see if you got the right one. I think you can do this. I know you can do this. So here's our next one. Again, you have a copy of this. Take out your copy. It'll be easier for you to see. I give you the formula. It's nice when I give you the formula because we can figure out how many hydrogen is missing. So again, number of carbon times 2 plus 2 is going to give me what? 4 times 2 plus 2. It gives me 10 hydrogen. But when I look over here, what? I only have 8 hydrogen. So I'm missing 2 hydrogen to get 8 hydrogen. So I know I'm missing 2 hydrogen. What does that mean? If I'm missing 2 hydrogen, I have a ring or I have a double bond. Not a triple bond because that would be 4, not a benzene ring. So a ring or a double bond, double bond is more common. But hey, I'm not gonna rule anything out just yet. That's what I get. Beautiful. Ooh, I give you an IR. That's good when you have an IR. Now let's look at the IR. What is IR telling me? When I look at the IR, I go, this is interesting. What is that? Ooh, that's an OH. That's a broad peak. That's an OH. That's great. And then, what is this? Oh, that is beautiful. That's a carbonyl. Okay. I know I have an OH. I know I have a carbonyl. And this is great because I have 2 oxygen to account for. And bam, I've already accounted for those 2 oxygen. I haven't even looked at NMR yet. But I know I have an OH and I know I have a carbonyl. And my carbonyl, is it carboxylic acid? No. Because if it was a carboxylic acid, you would get an ugly OH, as I would call it. Okay? So I know I don't have that. Okay, let's come over here. Let's come to proton NMR. Again, this is carbon NMR. We're not going to do carbon NMR. We are going to focus on proton NMR. Okay, let's look at this. How many peaks do we have? How many peaks do we have? We have 1 peak. This is just zoomed in. 2, 3, and 4. Again, these are just zoomed in. These peaks so you can see it better. Okay, I have 4 peaks. That sounds good. I want to look at peak A. Peak A is, let's look at a chemical shift. What can you tell me about a chemical shift? It's pretty downfield, isn't it? Yeah, this peak is pretty downfield. So if I had to bet money on this, I would say it's probably attached to an oxygen, right? My money would be safe. It's probably attached to an oxygen because oxygen is electronegative atom. So it's pulling the electron toward itself, which means the hydrogen doesn't have as much electron density. It can feel the magnetic field more, So it's going to be more downfield. It's going to be a larger ppm. Okay, good guess, right? Whoa, look at this. How would you describe this? How would you describe peak B? A bump? Yeah. So if you look at my lecture notes, when we talked about chemical shift for NMR, the first time we talked about it, I said, if you see a bump, what is that? That is usually OH or NH. And I know I have an OH. I know I have an OH. So the bump means that is my OH. So the bump is my OH. Okay. So I have my H on an OH already accounted for. That's pretty good. And if you remember, we said that could happen anywhere between 1 to 5 ppm. It's a large range. But what you're looking for a bump. All right. Beautiful. 2 peaks to go. 2 peaks down, 2 peaks to go. I look at C. I'm like, okay, that's good. It's about 2 ppm. Again, what does it mean if something is about 2 ppm? You already know that. When you have it around 2 ppm, that means that is next to a carbonyl, right? That means it's next to a carbonyl. Okay, so, and this is a CH3. So I have a CH3 attached to a carbonyl. Again, I'm thinking it's a carbonyl because at 2 ppm, usually when you're next to your adjacent carbon is a carbonyl, you end up around 2 ppm. So that's a good guess. Now, why did I say it's 3 hydrogen? Because again, don't forget up here. This is the integration. The integration is 3, so it's probably a CH3 attached to a carbonyl. I'm expecting a carbonyl anyway, so that makes sense. This one right here, what do I have here? I have a CH3. That's all I can really say right now, that I have a CH3. How do I know I have a CH3? Because the integration is 3. So, integration is 3. I have a CH3. That sounds good. Over here, integration is also 3. I have a CH3. ppm is 2. I know when I have around 2 ppm, it's probably next to a carbonyl. I want to put that down. I feel pretty good about that. Okay. Now, over here, the bump is OH. And this one is really downfield. It's about 4.5 ppm. So I'm going to say probably 4.2 ppm. It's probably directly attached to an oxygen. All right. Now, let's come over here to look at this splitting. What is this splitting for this? What is the splitting for this? The splitting is a doublet. If I have a doublet splitting, what does that mean about my neighbor? My neighbor has what? Has how many hydrogen? It has 1 hydrogen. So my neighbor has 1 hydrogen. So possibly I am attached to a CH. I am attached to a CH. Okay? So this is not bad. I got a lot of little things out of this so far. So I know that I have an OH. Why did that happen? I know that I'm directly attached to an oxygen. I know this piece. And I probably have a CH3 that is attached to a CH. Now we're going to put everything together. Now that's everything to put together. Okay. I said that I have a CH3 that is attached to a CH. And that is my peak D. Well, do you see any CH on here? Whoa, look over here. This is my CH. So could this be peak A? Possibly. Because I know, because of the splitting, this is a doublet. So this CH3 is attached to a carbon that has 1 hydrogen. So here is a CH and an N+1 rule. It will be a doublet. I show up with a doublet. Well, look over here. I have a CH right here. That probably could be that CH. It's a good guess, right? Now, that CH is directly attached to an oxygen. That CH is directly attached to an oxygen. And we know that in this case, it's directly attached to the OH. So this is my peak B. Now, how do I know it's OH? The IR told me I have an OH and I have a carbonyl. And this is directly attached to an oxygen, so the oxygen is probably OH. Okay. Now, I have this piece to account for, right? I have this peak to account for. So this is a CH, so 1, 2, 3 bonds. So it needs one more bond. So could this be attached to the carbonyl? Could this be attached to the carbonyl? Sure. So then this would be my peak C. Would this splitting make sense? Let's go over it. So over here, if this was good, the adjacent carbon has no hydrogen. So this would be a singlet. This is a singlet. Beautiful. Okay. This is my OH, broad. This is a doublet because the next neighbor has one hydrogen, 1 + 1, 2, doublet. Would it make sense over here? What does this one have? This one has a 1, 2, 3, 4. It has a quartet. Does that make sense? That does make sense because the next door carbon has 3 hydrogen. 3 + 1, 4. This is a quartet. That makes perfect sense. All right. So we have our structure figured out. Now, what I usually like to do, and I know you're probably really good at this, you don't need to do this, but it makes me feel better. I usually like to count the number of carbon and hydrogen to make sure I'm okay. So I go 1, 2, 3, 4. So I have 4 carbon. I want to actually count the hydrogen by hand, old school way. 1, 2, 3, 4, 5, 6, 7, 8. Because we don't want to make sure it match. And I have 2 oxygen there. All right. This does match, yeah? This gets another smiley face. A little creepy smiley face, but a smiley face. So that matched up pretty nicely. I accounted for hydrogen and for oxygen. The chemical shift matches, the splitting matches, and the number of hydrogen, the integration matches. Yeah? Okay, these are good problems. Ready for next one? Yeah. Let's do more practice problem. Okay, let's do this one. I mean, you're going to do this on your own, and then you're going to check with me. Again, I like it when I have a formula. Because then I go number of carbon times 2 plus 2 gives me what? 5 times 2, 10, plus 2 will be 12 hydrogen. Okay. Now, how many hydrogen I actually have? I have 10 hydrogen. So I'm missing 2 hydrogen. Okay? So I'm missing 2 hydrogen. So it will be 12 hydrogen if I have nothing but all single bond. But that's not true. I'm missing 2 hydrogen. So what does that mean? I probably have a ring or a double bond somewhere in there. Okay? It's a good piece of information to have. I give you IR. Ooh, that is good. I look at the IR. There are 2 things that stand out to me right away. What's the first thing? You go, oh no, ugly OH, right? This is an ugly OH. Now, I want you to kind of contrast it with the problem that we did, that was nice OH, right? This is a nice OH, nice and round. This is an ugly OH, it's just all over the place. We don't judge, but it's not as nice. So, I have an ugly OH, which means I probably have a carboxylic acid. Well, that's pretty good. I already know that I probably have a carboxylic acid. Good piece of information. And what is this? I have a carbonyl. So probably my carbonyl is the carboxylic acid. And this is great because now this is accounted for the 2 oxygen in the formula. Yeah, we are in a good shape right now. Again, this is carbon NMR. I just put it on there so you can see this carbon NMR, but we're going to focus on proton NMR. When I look over here, let's go label the peaks. I have a peak over here. I have a peak over, I have a peak over here. I have a peak over here, and I have a peak over here. Okay, these are not peaks. These are just the grids on a page. The one that have an integration, those are the peaks. All right, beautiful. Now, when I look at the peak at 12 ppm, look at that handout that I gave you about chemical shift. What shows up at 12 ppm? That is so downfield. What shows up at 12 ppm? At 12 ppm, that is the carboxylic acid hydrogen. I already knew that I had a carboxylic acid, but that's even better. What did I just write? Oh no, I was just testing you guys. Oh boy. There we go. Okay, that looks a little bit better. I want to show everything. Okay, so here is the hydrogen. Here is the hydrogen for carboxylic acid. IR told me I have a carboxylic acid. Now NMR confirmed it. Now I feel really good about this carboxylic acid. Again, this is not a peak. This is just the grids on the page. Okay, this is not a peak. This is not a peak. These are the peaks, the one that have hydrogen, number of hydrogen on top. Let's look at this one over here. It's about 2.2, okay? And it's a CH2. Now, what can you tell me about that? So you have a CH2 and it's about 2.2. So it's probably attached to a carbonyl, right? That's a good guess. This is probably attached to a carbonyl. Okay. Now, what do I have for C? C, I have a CH. I have a CH and it's a multiplet. So it's got a bunch of things around it. And D, I have 6 hydrogen. It's probably a CH3 and a CH3. That's all I know so far. Okay, so I know I have a carboxylic acid. I know I have a CH2 attached to a carbonyl. I know I have a CH somewhere, and I possibly have 2 CH3s. Now, let's put it together. Sometimes it's kind of like a puzzle. You have to keep putting it together and erase it and put it together and erase it, put it together until you get something that makes sense. And by makes sense, I mean it matches the chemical shape and also matches the splitting, right? It matches it a singlet, doublet, triplet, it matches up. So where am I even going to start on this one? What I'm going to start is actually I'm going to put down the carboxylic acid. That I'm sure. And I know this is A. I feel really good about this. The other piece of information I feel really good about is peak B, because that CH2 has to be attached to a carbonyl. So I feel pretty good about this, right? Because we say it's probably attached to a carbonyl, and our carbonyl is carboxylic acid, right? I have one carbonyl, I have one double bond in the entire compound. This is that, and then the CH2 would be attached to that. All right, so far so good. Now, what's going to be after that? I want you to look at this CH2, peak B. What is the splitting on that one? The splitting on that one, it looks like a doublet, okay? So the splitting, it looks like a doublet. So I have no hydrogen over here. So if it's a doublet, that means the other neighbor should have how many hydrogen? It should have 1 hydrogen, right? N+1 rule. It should have 1 hydrogen. Okay. That possibly could be our peak C. Not eliminating anything just yet. Then what I have at 1 ppm, I have possibly 2 CH3s, right? They're equivalent to each other. That's why I have one peak for it. And it's a doublet. If it's a doublet, that means the neighbor has one hydrogen. Well, look over here. Doesn't that have one hydrogen? It does have one hydrogen. So, is it possible that I have a CH3 and I have a CH3? So, these are my peak D. That's really possible, right? Okay. Now, let's look at the splitting a little bit more to make sure this makes sense to us. Carboxylic acid, absolutely. Confirmed, confirmed. Over here, I know this is a peak next to a carbonyl. Peak next to a carbonyl is usually downfield around 2.2 ppm. I have that over here, okay? So that is going to be my CH2 attached to a carbonyl. And again, remember, you have 2 oxygen in this whole compound, and you've already accounted for those 2 hydrogen. So this will be attached to this carbonyl that it has. That makes sense, because then it has a doublet. So this side has no hydrogen, and this one has 1 plus 1, 2, so I get a doublet. Now, this CH, I know is attached to a CH2. I have 2 CH3 to account for. It's probably attached to those 2 CH3s. Now, let's see if the splitting makes sense. If I'm looking at the splitting for this one, it's a mess, isn't it? Because HC is next to CH2 and then is next to CH3, CH3. Now CH2, that's my peak B, and these are my peak D. So these are not equivalent to each other. So if it's not equivalent to each other, we can add it together. It would be N plus 1 times M plus 1. So then what I would get, 2 plus 1 from one side. And then these are additive. I can add these 2 together because they're equivalent to each other. 6 plus 1. Oh my goodness. So that would be 3 times 7. That means that's a huge multiplet, right? What do I have here? I am going to have a lot of peak. Is that what you see here? Yeah. Look at that peak. It's just got too much going on. That's kind of what I expected, to have too much going on because it's surrounded by adjacent carbon that have hydrogens. Okay, that makes sense. I'm feeling good about that. Am I feeling good about D? Definitely feeling good about D. They're equivalent to each other, and then the adjacent carbon has 1 hydrogen, 1 plus 1. I get a doublet over here. I feel good about this structure. How about you guys? Now, even though I feel good about it, I'm still going to count the carbon and everything to make sure I am right on, because you cannot lose any carbon or gain any carbon. Carbons do not grow on trees, my teacher used to say. 1, 2, 3, 4, 5. Okay, 5 carbon. Again, I'm going to be old school. I'm going to be counting the hydrogen to make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yay! Okay, and I have 2 oxygen. That does confirm it. That does match up, which is nice. Yeah? All right. Very nice job. Very, very nice job. So, next review session, we're going to do 3 more practice problems to make sure you are getting this down. Now, if you have time, do the rest of the packet on your own. So the next time when I'm going over this, you're ready to listen and hopefully our structures will match. Thanks for hanging in there with me. I will talk to you guys next time.